All right, we're going to take a look at solving exponential equations. Now, of course, an exponential equation is an equation that has these new exponential functions that we've been seeing in it. So something that may look like 2 to the x is equal to 8. Right, exponential equation because we have our variables are in the exponents. Now we're going to see one basic way to do this, but there is kind of a side note on how we can handle a few of the more simple ones like this. It's a property, it's an equivalence property, and it says if you have a to the x equals a to the y, right? If you have the same base and they're equal to each other, well then the exponents should also be equal to each other. So if in some way we were able to write both sides using the same base, then we could just equate the exponents and solve what's left over. So in this case, we could write both sides using 2 as the base. Of course, that already has a 2, and we can write that as 2 to the third. And of course, here you can see x is equal to 3, which should have been obvious from the beginning because it said 2 raised to what power is 8. Now, another one that might work something like this, what if I said 8 to the x is equal to 4? The same idea, but a little bit different. Can we write both of these numbers using the same base? And we can. 8 is 2 to the third, and 4 is 2 squared. Now notice on this side we have a power raised to a power, so we have to multiply that. Now that we have the same base, we can equate the exponents. So we have 3x is equal to 2, so x has to be 2/3. All right, so this is one way to solve an exponential equation, but it doesn't really help that often. So we need a more all-purpose method on how to do this. And since what we need to do is get the exponent kind of down so we can solve for it, we're going to use logarithms. So let me go ahead and give some steps for this. Since it's an equation, we always have steps. Step 1, isolate the exponential. Step 2, take the log of both sides. Now, I'm going to give you a hint. We're going to do this different than a lot of textbooks do. Here we're going to use the same base as the exponential. Okay, so what that's going to let us do is bring down any exponents and simplify. Let's see, once we bring down all the exponents and simplify, all we have to do is solve whatever equation that we have left. All right, so let's take a look at something like this. 5 to the x is equal to 7. Now notice we can't use the same trick that we did over here, or at least not very easily, right? We can't write 5 and 7 as some number to a power. So to solve this, what we're going to do is we're going to take the log of both sides so I can bring that exponent down in front. Now since the base of the exponential is at 5, I'm going to use log base 5. You'll see why that's helpful in a second. So log base 5 of 7. Now technically you can use any logarithm here that you want. It just makes the next step a little bit easier. Now we can bring down the exponents and simplify the logarithms. Now the reason I picked the same base is because now this piece, log base 5 of 5, or what do you have to raise 5 to get to 5? Well, that's just 1. Now over here, this says, what do you have to raise 5 to get to 7? And I don't know, 1 point something. All right, so there you go. So from this point, if we wanted to figure out what that value is, we'd have to go to our calculator and use the change of base formula to figure that out. All right, let's try a couple more of these. So let's say if I had 3 to the 4x plus 2 is equal to 6. All right, this is an exponential equation because we have variables in the exponent. So let's follow our steps. First step says isolate the exponential. This is our exponential. It's on the side all by itself. Take the log of both sides. All right, so let's take the log. And since the exponential is base 3, I'm going to use log base 3. Now the reason we do this is so we can bring down our exponents. That's log base 3 of 3. log base 3 of 6. Now the reason I use base 3 is now this will simplify. This gives me 4x plus 2 is equal to log base 3 of 6. I'm not sure what that is, right? Again, 1 point something. All right, now we got to solve for x. Now remember, this is just some number. It's just a number I'm not sure what it is. This is just a linear equation. So let's subtract 2 from both sides. Now when we subtract numbers from logs, I'm going to erase this. We generally don't subtract it out here because you tend to do something like 6 minus the 2. Remember, that's not a 6, that's log base 3 of 6. So a lot of times you'll see the numbers written out in front of logs. So that's negative 2 plus log base 3 of 6. Divide both sides by 4. So x is equal to negative 2 plus log base 3 of 6 all over 4. All right, again, if you wanted a decimal approximation for this, you'd have to use your change of base formula for this. Now, unfortunately, a lot of textbooks here teach always use the natural log, which there's absolutely nothing wrong with that at all to always use the natural log. All that means is your answer is going to be a little bit more difficult to realize that it's the same thing. Because if you would have done this with the natural log, you actually would have got negative 2 ln 3 plus ln 6 all over 4 ln 3. All right, so notice that this answer looks completely different than this answer. So if you get an answer that uses a different base than what the answer in the back of the book is, the quickest way to do it is to grab your calculator, put both of them in there and see if it's the same number. Now, how do I get from this answer to this answer? Well, if you rewrite this, I'm going to squeeze it in right here and I'm not going to do all the steps. If I wrote it as negative 2 plus, and if I use my change of base formula for that, that's the natural log of 6 over the natural log of 3. Then if you clear your complex fractions, you'll get to this. So there is an algebraic way to get from our answer to most likely what the book is going to have, but it can be a little bit messy. All right, let's try another one. And I need a little bit more room here, so let's say if I had 3 to the x plus 1 is equal to 4 to the 2x minus 3. All right, a little bit more complicated this time. Again, this is still an exponential equation because we have variables in the exponents. Step 1 says isolate the exponential. However, I have 2 exponentials, but each one is on a side by itself, so it should work. The next one says take the log of both sides. I can do that, but I said use the base as the same as the exponential. I have 2 different bases here, so we actually have an option. You want to use log base 3 or log base 4. Now there's no wrong choice here, but I generally suggest use the base of the exponential with the more complicated exponent. So I'm going to say this one's a little bit more complicated, so I'm going to do log base 4. Log base 4 of 4 to the 2x minus 3. This allows me to bring down the exponents. 2x minus 3 log base 4 of 4. And then try to simplify the logarithms. I'm not sure what log base 4 of 3 is, so that one has to stay. Over here, log base 4 of 4 is just 1, so that's 2x minus 3. All right, I know that this looks scary, but think about it like this. If this was the equation, x plus 1 times 7 is equal to 2x minus 3, I'm guessing all you could solve that fairly easy, right? Distribute, get all your x's to one side and on the other. The only difference is I don't know exactly what this number is, but that doesn't mean my steps are going to be any different. So what are we going to do? We're going to distribute here. So this is x times log base 4 of 3 plus 1 times log base 4 of 3, 2x minus 3. We need to get all of our x's to one side, everything that doesn't have an x to the other side. So let's move our x's over here. So I have x log base 4 of 3 minus 2x plus log base 4 of 3 is equal to negative 3. Let's move everything that doesn't have an x to the other side. So I'm subtracting log base 4 of 3. Log base 4 of 3 minus 2x is equal to negative 3 minus log base 4 of 3. Now I got all my x's on one side, everything that doesn't have an x on the other side, I need to divide by what's in front of my x. The problem is I have two terms with an x. We've seen that when that happens, we factor out the x, minus 2. And then all we have to do is divide by whatever's in front of our x. So we got log base 4 of 3 minus 2, log base 4 of 3 minus 2. All right, so x is equal to negative 3 log base 4 of 3, log base 4 of 3 minus 2. All right, so when we have two exponentials, it is a little bit more difficult. Pick a base, whichever base you want to do, take that log of both sides, break down the exponents, then most of the time it's a linear equation. Now it looks uglier than a normal linear equation, but it's the same. Get all your x's to one side, everything that doesn't have an x to the other side, factor out your x if you need to, then divide. All right, there's one more type of exponential equation that you'll see in this section, and it might look something like this. Let's do e to the 2x plus 4e to the x minus 12 is equal to 0. All right, this is an exponential equation because we have variables in our exponents. However, these steps won't work because there's no way to isolate the exponentials. We have two of them, but we can't get each one on the side all by itself because we have this 12 here. So what this actually is, if you may recognize, it has three pieces. It almost looks like our quadratic form. And if you think of e to the 2x as e to the x squared, remember, power raised to a power you multiply, this has quadratic form. So if you let u equal e to the x, you can see u squared would be e to the x squared, which if you want to see, that's e to the 2x. So by plugging that in, what we end up with is u squared plus 4u minus 12. All right, this is just a quadratic equation. Solve this any way that you can. I believe this one will factor, unless I've made a mistake. Let's see, two things that multiply to give me negative 12, but add up to be positive 4. That should be plus 6 and minus 2. All right, two things multiplied together equaling 0, so either u plus 6 is equal to 0, u minus 2 is equal to 0. So we get two values for u. We get u is equal to 6 and u is equal to 2. Now remember with these u substitution problems, we have to always back substitute. So let's go back up to here. We get two equations, u is equal to 6 and u is equal to, what did I say, 2? All right, u is e to the x, and e to the x is equal to 2. All right, so now basically what we've done is we've separated this into two exponential equations. So now we can use these steps. Isolate the exponential, that's done in both of those. Take the log of both sides. Now since the base is e, I'm going to use log base e. And remember, log base e of something is just the natural log. So I'm going to do the natural log of e to the x is natural log of negative 6. The natural log of e to the x is the natural log of 2. All right, then we bring down our exponents. Natural log of negative 6, x natural log of e, natural log of 2. And then simplify. Now remember, this is really the natural log of e is the exact same thing as log base e of e. So what do you have to raise e to get e? Well, that's just 1. So here we get x is equal to, and we want to try to simplify the natural log of negative 6. However, remember, we're not allowed to take the logs of negatives, right? So this does not work. So this doesn't give us an answer. Let's go over to this one. The natural log of e is 1, so we get x is equal to the natural log of 2. Now, I don't know what the natural log of 2 is, but it is just a number. So there's our answer. All right, so you're going to see a few of these in the homework where they have quadratic form. The easy way to tell is they have 3 pieces to them. If that has 3 pieces, generally you're going to do a u substitution for quadratic form. All the other ones, your steps should work for you. Isolate the exponential, take the log of both sides, bring down the exponents so you can simplify, and then solve whatever's left over.